Hi everyone. It's the last session of the day. Thanks so much for being here, your hardcore SQL Bits participants. My name is Jakub Szymaszek. I'm program manager in security and governance team. We are part of Azure Data Platform team, and we are responsible for building, providing security technologies for all Azure data products and services that include SQL Server, Azure SQL Database, Cosmos DB, and Postgres MySQL. So one of these technologies we're gonna cover today is always encrypted with secure enclaves. It's one of its kind encryption feature because it combines two kind of goals that are conflict with each other. So it protects data from high privileged users and at the same time providing confidential query capabilities. And it's also one of our more complex technologies, which is why we propose this session to demystify and uncover, explain some of these complexities. Before I start, let me take a quick poll. How many of you know, are familiar with Always Encrypted in general? Okay, everybody, great. So I'm asking because this is an advanced session. We're really going to go into details and many technical aspects. So that's great that you already have some background. So I was going to spend a few minutes recapping on the basics, but I will go through it still very, very quickly. And then we'll jump straight into what enclaves are and how we use them in SQL Server. And we'll cover query processing workflow. We talk about indexes on encrypted columns, how they are implemented and how you can use them. And we'll talk about performance. I will share some performance benchmarking results with you. And performance will be one of the main themes that will kind of show up here and there in various points of the presentation. So let's revisit very quickly the motivation behind this feature, which applies equally to Always Encrypted, the classic version, the initial version, as well as its flavor using enclaves. So the main goal, the main motivation is to protect the data from high privilege but unauthorized users, database administrators, cloud operators. So that's the main objective. As you know, the existing or other technologies like TD, TLS, and other controls do not really protect the data from high privilege administrators or high privileged users in general. The second goal is to allow customers to confidently move their data to the cloud. Migrating data to the cloud means that you're giving up control, right? You outsourcing DBA roles to a cloud provider, right? So the goal of this feature is to make sure that you retain the control. And we do that through encryption. And finally, what makes this feature really unique is that we are trying to achieve what has been impossible until this feature has been supported, and at least it wasn't really common or possible in commercial database systems. We try to support confidential computations, confidential queries on the data that is protected from administrators, right? And revisiting this classic initial architecture of Always Encrypted, now it is available generally in SQL Server 2000, since SQL Server 2016, Azure SQL DB managed instance. The thing you might not know is that it is also now available in Cosmos DB in preview. So we started expanding Always Encrypted to other data platform products and services beyond SQL as well. And three basic things we typically share about as basic characteristics of Always Encrypted. Number one, it's a client-side encryption solution that's fundamental to provide these strong security benefits we talked about on the previous slide. So the data is not even exposed in plain text on the server side. So even if the server is completely compromised, an attacker cannot really even see the data in the clear. Encryption transparency is achieved by the client driver that transparently translates between plaintext and ciphertext, and we'll go over the details of how that works exactly. And finally, the thing I mentioned earlier, confidential computations. In this initial version, they were provided, supported in a very basic form. We namely managed to support one type of confidential computation, that's equality comparison through deterministic encryption. And the moment we shipped that feature, we knew that it's gonna be limited, right? Because many application workloads, many database workloads need much richer functionality in SQL queries than just equality comparison, pattern matching, range comparisons, and so on. So we decided to expand this basic architecture, but by allowing the data to be decrypted on the server side. But of course, decrypting it in the SQL Server process memory without any changes to the architecture would mean that we compromising the security value of the feature, right? So what we did instead, we allowing the data to be decrypted inside a special place, which is called a secure enclave. It's basically a black box, a secure container that the content of which is invisible, inaccessible to anybody on the machine running SQL Server, including the containing process, including the DBAs or OS system administrators, right? So why do we allow the data to be decrypted? Well, because so that we can, or the SQL Server engine rather, can perform computations on the data in the clear within that secure boundary provided by Secure Enclave. And with that, we can support richer queries, including pattern matching, range comparisons, sorting, and we also support indexes, which is an important aspect we'll get to in a second. And we are addressing an operational problem of this initial architecture we talked about on the previous slide. If you have used Always Encrypted, you know that one challenge that customers face today is that if you have a large table, you want to encrypt a column, right? We give you the tools that load the data in that table containing that column to the client side, perform cryptographic operation, and upload the data back to the server, right? So it's a very painful process that is prone to network errors and multiple other issues. So with enclaves, we can support such cryptographic operations, including key rotation and initial encryption in place inside the enclave. No need to move your data outside of the database, right? So this is at the high level what Always Encrypted with and without enclaves is. Any questions so far? Okay, that's pretty straightforward. Cool. So let's talk about enclaves, what they are exactly and how we use them. Again, this is pretty basic. You might know that already. So an enclave is a chunk of memory with very special, unique properties, right? It's basically an isolated region of memory that even the containing process that contains this region of memory, it cannot see what's inside it. So it cannot see the code or the data that is contained within the enclave, right? So therefore, an enclave is naturally a great trusted execution, a great candidate to be a trusted execution environment for processing your sensitive information, because even admins on the machine cannot see what's inside the enclave. And an enclave is a general concept, and it can be implemented or realized in several different ways using different enclave technologies. And in SQL, we use two enclave technologies. In SQL Server 2019, 2022, we use virtualization-based security enclave, or in which the entity that ensures these isolation properties of the enclave is Windows hypervisor, okay? And in Azure SQL Database, we use hardware enclaves provided by Intel technology called Intel SGX, or Secure Software Guard extension. So in this case, Intel CPU is the guardian of the enclave security and the provider of the enclave isolation, okay? For you as an end user, it doesn't really matter much. There are some differences in how you configure Always Encrypted with secure enclaves in SQL Server 2019 versus SQL DB. But from the functional point of view, the surface area, the set of supported queries, it's the same, okay? So now diving a little bit deeper, this is how SQL Server is architected internally regarding how, from the enclave point of view, if you will. So we partitioned the code base of the SQL Server process into two parts. The vast majority of the SQL Server code base runs outside of the enclave, and that includes the main query processing workflow, loop, buffer pools, lock and latches management, things like that. Inside the enclave, what runs inside the enclave is a very, very tiny part of the SQL Server code base, which basically implements a set of predicates that we want to support in a confidential way. So that includes, for example, like predicate or comparison operators, less than, greater than. And the way it works, the way this query processing is partitioned between the untrusted and trusted part, where the trusted part is contained within the enclave, is, again, the main query processing happens outside of the enclave. As in this example, let's say we have a pattern matching query. We're trying to find a person with a given social security number based on the prefix or a suffix. What it would do, let's say you have a table with 1 million rows, right? And there is no index, right? So let's assume that. So then the main query processing workflow on the left-hand side would basically trigger 1 million calls to the enclave, right? Passing the encrypted operands or parameters of this pattern matching evaluation. And the enclave would decrypt, the parameter of the query and a single value that comes from this table, and would evaluate the like predicate and return the partial results to the main query processing loop running in the untrusted part, right? So that's how it works. One thing to know, again, as I said, performance is one of the themes of our presentation here. You need to know that calls to the enclave are somewhat expensive. They are more expensive than normal function calls, right? So you really should be thinking about ways how to minimize the number of these calls. And one way to do that is by configuring properly indexes on the columns you are querying, right? And you can logarithmically decrease the number of calls to the enclave. That's why we strongly recommend that you create indexes on encrypted columns if you run enclave queries, and we'll talk about indexes in a second. Any questions? Any questions online? Okay, cool. The other concept that is very important for Always Encrypted with enclaves is the concept of attestation. So enclaves are these great benefits. We can support richer queries with them, but they also are the source of complexities, right? So one complexity is related to the following question, okay? So let's say you have this client application on the left that is using the enclave on the right, and the enclave is contained in the SQL Server, which could be compromised by an attacker. That's our threat model, right? So now the question is, how does this client application on the left actually know that this enclave on the right is trustworthy, that it hasn't been compromised, for example, replaced by an attacker with a malicious binary that now reveals your data, right? So we don't want that to happen, and that's why we introduced the concept of attestation and the attestation protocol, which allows the client application to verify the enclave is trustworthy before authorizing its use for query processing, right? So that's a high-level idea, and now drilling down a little bit and using a specific example, this is how this is implemented in Azure SQL Database, where we use SGX enclaves, and for attestation, we use a specific Azure service called Microsoft Azure Attestation. Its sole role is to support attesting various trusted execution environments, including enclaves. And it's a service that basically evaluates enclaves against policies. And we provide you with a template of such a policy in our documentation. And what this policy does, it basically verifies the enclave binary and its specific properties. For example, this MR signer field is a hash of Microsoft signing key, right? So this policy verifies whether this enclave has been signed by Microsoft or whether it has a specific product ID that has been assigned to it, right? Or that debugging capabilities are turned off. Otherwise, the enclave would leak your data to the environment, right? So it's a declarative model. That's how it works in SQLDB. And we'll come back to share more details about how this works exactly step by step. Now, let's talk about query processing workflow, how it works between how it is spread and how it works, starting from the application through the client driver and involving SQL Server Engine. Before we do that, though, we need to talk about encryption metadata that is stored in SQL Server, because this query processing is actually driven by the metadata that SQL Server, your database, stores about various things, including encryption keys, right? So in Always Encrypted, you know that already probably. We use a two-level key hierarchy. We have column encryption keys, which are used to encrypt data, and we have column master keys, which are used to protect column encryption keys, right? So it's a two-level key hierarchy. And in the database, you store the metadata about both types of these keys. But this metadata never includes the actual key material, right? So the column master key metadata object only references the real master key, which is stored outside of the database, for example, in Azure Key Vault, right? The column encryption key metadata object contains the encrypted value of the key, never plain text, right? And now, what we did with enclaves, we introduced the new concept of enclave-enabled keys. An enclave-enabled master key is the one that has this enclave computations property set in the metadata. And an enclave-enabled column encryption key is the one that has been encrypted with an enclave-enabled column master key, okay? And now only enclave-enabled keys can be used for enclave computations. So this is important, and you will understand why when we talk about, when we cover the metadata for columns that are encrypted. So again, this is an example of the create table statement. This is how you define encrypted columns. You use this encrypted with clause. And when you do that, you specify the algorithm, which for encrypting your column, your data in your column, and there's only one option for now at least, AES-256. You specify encryption type, which can be deterministic or randomized, and you specify the key that should protect the data in this column. And again, if you use an enclave-enabled key, that means that for this column, enclave computations are supported, right? So in general, we have 3 levels as far as level of confidential computing on your columns is concerned, right? And the set, what you can actually, which computations you can trigger on your columns depend on 2 factors. Number 1 is the type of encryption, deterministic versus randomized. And number 2 is whether the key that has been used for the column is enclave-enabled or not, right? So let's say you have chosen randomized encryption and the keys that are not enclave-enabled. Then you cannot do any computations on those columns at all. And this is still a great choice, perhaps for scenarios in which the processing of the data stored in this column happens only on the client side. You don't need database to do any computations on the data. Then you have deterministic encryption. And again, this is the traditional option which existed since the initial version of Always Encrypted. Great option if all you need to do is equality comparison and point lookup searches, equality joins, stuff like that, right? But then if you truly want to unlock the full power, all the capabilities that Enclave provide, you have to configure randomized and as the encryption type, and you need to make sure that a key that protects your data is Enclave enabled, right? So then you have ability to run range and like queries, and actually let me double click on that. So here is the list of all computations, all predicates and operations that you can run on enclave-enabled columns, if you will. One important thing I want to call out for those of you who use SQL Server on premises or in Azure VMs, we've made some enhancements in SQL Server 2022. Mainly we support all kinds of joins, including hash and merge joins now, and we support order by and group by clauses, as well as we support UTF-8 collations, which allow you to do case-insensitive searches. For example, using pattern matching or and the like predicate, or even equality comparison. That has not been possible. That was not possible in SQL Server 2019. Okay. All right. Okay, so let's talk about the query processing workflow after we understand how all this metadata is defined and constructed. On the right-hand side here, we have a table with 2 columns encrypted, name and social security number. On the left-hand side, we have an application that triggers, a point lookup query. So there is no enclave in the picture. As you might know, what happens in this case, the first thing that happens is the client calls this special STOR procedure called SP-describe parameter encryption, which is a discovery call, if you will. This prompts SQL Server to compile this query statement and detect any parameters that correspond to the columns in the database that are encrypted, okay? And if the server finds any parameters corresponding to encrypted columns, it returns the metadata about those columns. And the first thing that the client driver does, that metadata includes key information, it contacts the key store containing the master key and decrypts the column encryption key, right? So now it has access to the column encryption key. And subsequently, it uses this key to rewrite the query statement logically and to basically encrypt the query parameter that corresponds to encrypted column. Now, assuming SSN is encrypted using deterministic encryption, SQL Server can find the matching name. In this case, we're looking for a name corresponding to the social security number. Since the name column is encrypted too, all the metadata along with the result is returned to the client driver, which, as before, can use this metadata for cryptographic operations. In this case, it decrypts the name and returns plaintext to the application, right? So 2 main takeaways here. Number 1 is because of this metadata, we make these cryptographic operations transparent. The client driver doesn't have to, the application developer rather, doesn't have to know which columns are encrypted, which are not. The client driver figures that out on behalf of the application. And the second thing is again about performance, right? So this transparency is achieved because of this extra round trip that the client makes to the server, which of course is costly potentially. So one thing that we did in two main drivers, JDBC and ADO.NET, we implemented the optimization called parameter metadata caching, which means that this round trip is only made for the first execution of the given query statement. And then we cache the results so that we minimize the number of these calls, okay? Now, let's double click. So that's how it works without enclaves, right? So now, let's introduce attestation into the mix, and let's see how attestation and enclaves change this basic query processing workflow. So let's say now you run a slightly different query that does the pattern matching on the SSN number, right? So to process this query, we need to use the enclave, right? So again, the driver will issue a SP-describe parameter encryption as before, no changes to that. But the difference is now that the server will figure out, okay, to process this query, I will need to use the enclave. Therefore, it will collect all the property values of the binary that runs inside the enclave. and sends it to the attestation service, which will evaluate it. It will issue the attestation token, which confirms that the enclave property meets the policy criteria and the policy that is configured in the attestation service. That attestation token is sent back to the client driver, which verifies it. It verifies it by loading the public key from the attestation service and basically verifying that the attestation token has been signed by the attestation service. And only after that, the client driver will permit the query processing to continue, will actually submit the query to execution after this verification is successful, okay? Does that all make sense? Okay. The other thing that we need to solve is, so I mentioned to you a couple of times that the enclave decrypts the data, right? In order to process it in plain text. So you might ask a question, wait a minute, but the server doesn't have access to the keys, so how does the enclave get the keys, right? So the answer to that is we have implemented the key release protocol, in which the client driver shares the keys with the enclave. This happens, again, as part of this SP-describe parameter encryption call. The enclave and the client driver then negotiate a shared secret using the Diffie-Hellman protocol. And then the client driver encrypts the column encryption key with the shared secret, sends it to the enclave, and the enclave has the key, can use it for cryptographic operations. So that's how it works. Okay, let me show you a quick demo, which kind of puts all these ideas and concepts together. So for my demo, I'm going to use the example you might be familiar with. It's been used in a couple of other demos today and yesterday. The Contoso HR example. Here I'm containing to the database that stores employee human resources records, and as a DBA, I can see all the data in the clear, right? So that's our starting point. That's the problem we want to solve. We actually don't want the DBA to have access to the data in the clear. So how do we do that? Let me kind of walk you through the steps needed to set this up, right? So this is my environment, my resource group in Azure, which contains my database, okay? It contains my attestation provider in Microsoft Azure Attestation I have already provisioned, and it contains my key vault with my master key, okay? So let's look at the configuration of these three key components. In Azure SQL Database, as I mentioned, we use hardware enclaves, right? So a prerequisite here is you need to make sure that you configure your database in a way that ensures that it runs on hardware that supports Intel SGX enclaves, right? Which means that you need to pick this special hardware configuration. We named it DC series. And when you do that, your database is placed on SGX-enabled machine. And only then enclave functionality is unlocked, available to your database. So that's one prerequisite. Then I need to configure the attestation provider in Microsoft Azure Attestation and hydrate it, configure it with an attestation policy, the same one I showed you on the slide before. And finally, I need a key vault to contain my master key, okay? Again, I pre-configured it already. And as a person who will be configuring and encrypting my data, I need to have access to that key, so I need an access policy, or I need it to be in a specific role for this Azure Key Vault instance, okay? So let's say I have all that. Now I can actually configure the metadata for my keys, which I have already done, and I can show you how it looks like. So here I'm querying the views containing information about keys, and you can see that I have provisioned the column master key object, and I have configured configured it as an enclave-enabled key, so it has this allow enclave computations property or flag set. That's important if I want to unlock the enclave functionality for the queries on the data that I will be protecting in this database, okay? So now I'm ready to encrypt my data. And with enclave-enabled keys, with enclaves, I can do that in place simply by running alter table statements like examples that you see in this sample script. One other prerequisite, one other thing that I need to do, I need to make sure that I'm connected to the database in a special way. So let's actually see this in the Always Encrypted tab of the connection dialog. So I need to, of course, enable Always Encrypted for the client driver that is used for this connection. And I need to specify the enclave attestation URL, which points to this attestation provider in Microsoft Azure Attestation. After I've done that, I can run this script, and it should encrypt my the 3 columns that I'm specifying in these 3 statements in place inside the enclave, right? So now, if we switch back to the previous instance of SSMS that I used here, which I was using as a DBA, right? This is what I saw before. When I rerun this query statement, I'm going to see the 3 columns encrypted now, right? So now, on the other hand, if we go back to the SSMS instance that a person who has access to the keys is using, the same query, of course, will return different results. It decrypts the data transparently, showing me plaintext, because here I have access to the keys, and as a DBA, I don't have access to the keys, right? And I can also run richer queries, including range comparisons or pattern matching. And again, these queries use the enclave under the covers, okay? So let's go back and talk about one more or couple of more concepts or topics. One thing I want to touch base with you on is indexing, right? So we actually, the main complexity of this project and this feature on our side was to implement and support indexing or encrypted columns. But let's take a step back first here. So let's say you have columns using randomized encryption and regular keys. You cannot create any indexes on such columns because you don't need them, right? Randomized encryption with regular keys doesn't support any queries, so no indexes are needed. If you're using deterministic encryption, then you can create cluster, non-cluster indexes on columns using deterministic encryption. What's important about such indexes, they are sorted based on ciphertext, right? Because that's what deterministic encryption operations are about. They involve comparing ciphertext, right? On the other hand, if you have a column that uses randomized encryption and enclave-enabled keys, and if you create an index on such a column, the sort order in that index is based on plain text, right? So the data is sorted based on plain text. And this has some important implications. It basically means that if I want to create an index on a column that uses randomized encryption and enclave-enabled keys, the enclave will need to be involved in sorting the data, right? Because it's sorted based on plain text. And the implication of that is that somehow the enclave needs to be provided with the key, okay? And in general, there are 2 ways to do that. I can basically connect to the SQL Server with Always Encrypted enabled. But that's not so interesting, because that means that me as a DBAs typically create indexes, right? I would need to have access to the keys. So that would defeat the purpose of using Always Encrypted if the goal is to protect the data from potentially malicious database administrators. So that's why we introduce another way or method for the enclave to get the key for indexing operations. Basically, the enclave has a cache in which we cache the keys used for previous queries. So if as a DBA, I can run basically create or alter index statement, and that statement can use the keys that have been cached provided to the enclave as a result of running previous queries. So through that, we can achieve separation of duties, right? As a DBA, I can manage indexes without having access to the keys. That's how we achieve that. Any questions?
Assuming that it has to be someone run against it before I can create an index, because otherwise the key won't be in the cache.
That's right. So the question is confirming somebody needs to run a query that hydrates the enclave with the keys before I can create an index. The answer, yes. The answer is yes to that. The longer answer would be that yes. So normally you are assuming that an application workload has run the enclave query before, and the enclave has the required key. We also introduce a special store procedure, which is sp send enclave keys or something like that. So, you know, as a DBA, you can ask a security administrator who has access to the keys to run this store procedure, and it will send the keys to the enclave. Okay. As an alternative way to provide the keys to the enclave. You can either run a normal query, like pattern matching, that will send the key to the enclave, or you can run this extra special store procedure to do that too. We short on time, so let me quickly jump here and just talk for a couple of minutes about the benchmarking results that we have done. So what we did is, are you familiar with TPCC benchmark? You've heard of it, okay? It's basically a standard, traditional, very popular benchmark that simulates a transactional workload, right? So, and it triggers basically a bunch of purchase order transactions, right? So it's basically a simple e-commerce application, right? So what we did is, we measured the throughput in this benchmark, how many transactions we can run in a unit of time. And we ran this test in 4 variations, right? Or we had 4 different runs. In run number 1, there was no always encrypted in the picture at all, right? And you can see the results of that and represented by this first bar. Then what we did, we just enabled always encrypted in the database connection string. So no columns encrypted. We just tell the driver, okay, we enabling turning the always encrypted functionality inside the driver, right? So what that triggered, the driver started sending these extra round trips to the server, right, for each parameterized query, although because of course it didn't know there was no column encrypted on the server side. And you see a substantial degradation here. I do want to recall what I said earlier, which is that, so we did this test with the driver that didn't support this optimization I mentioned to you earlier, right? So it didn't do any caching. In .NET and ODBC driver would have this caching implemented now, so you wouldn't see the difference would be much, much smaller between bar number 1 and bar number 2. And then the next thing we did, so now we encrypted about 30% of PII columns that are contained in TPC benchmark, like customer names, addresses, phone numbers, right? And we encrypted that using deterministic encryption. So now about 30% of transactions were actually triggering point lookup search using deterministic encryption on a number of columns, okay? And you can see that performance decreased by about 12% or so. And now in the 4th run, we replace this deterministic comparison on ciphertext with comparison using plain text inside the enclave, right? And the performance dropped by maybe 10 to 15%. So the difference between 3 and 4 is what you care about when you want to discuss the impact of enclaves on query performance, right? So one could argue it's not very substantial. I do want to mention one very important thing though, right? The benchmark, these results that you see here, these are not results measuring the performance of individual queries, right? They measure end-to-end performance of a workload, right? And in this workload, a small number of queries hit the encrypted columns, right? And very few columns, relatively speaking, are encrypted, right? And that's adheres to best practice that we, in general, recommend to customers. You should not use this feature to encrypt all your data in your database, right? You should use it conservatively and encrypt really the data that you truly care about in terms of data that is really, really sensitive, right? That's how the feature is designed to support. That's what the feature is designed for right now, at least. Okay. So, yeah, we out of time, but a couple of next steps I'd like to suggest. There are docs, of course. There is one good research paper which this presentation was heavily based on, this SIGMOD paper we published a year ago. It has even more details if you're interested in them, about how the feature is implemented, and also it captures the performance results that I went over in this presentation very quickly. We have the demo that is published on GitHub. If you haven't tried enclaves yet, this would be a good starting point. We already had a couple of security sessions by folks from my team. One remaining is tomorrow's session by Andreas. He will cover other security improvements that we've made recently, so you might be interested in joining that as well if you're passionate about security. It looks like you are, since you are here with me. So with that, I'm happy to take any questions you might have. Please complete the evaluation form as well for me. Thank you.